Okay, everyone, I think we can start. We are already recording. So I will probably leave the camera like this so that you can see the audience, Felipe. If
Yes.
the internet is not very good, I will probably switch this camera off. Okay. It is
Okay.
a great pleasure to have my friend Felipe from the Benemérita Universidad Autónoma de Puebla. So he works in the GrainsLab in the Physics Institute, and he's going to give an overview of all the work that he's been doing in the past few years involving granular materials. It was a pity that Felipe couldn't make to our workshop, but he will come in another opportunity for sure. But he will be here with us today in the video, so we are going to see how things, the things that he is doing in his lab. Okay, so Felipe, it's
Yes.
it's you can start. You have the word now. Go ahead. It's very nice to have you here.
Thank you very much, Yuri. Okay. Well, as Yuri explained, I'm coming from the Institute of Physics of the Autonomous University of Puebla in Mexico. And well, first of all, I would like to thank Yuri for the opportunity to present my work in this summer workshop. Even when it is in mathematics, but I'm more working only in topics related to physics. Okay, so anyway, we need physics, mathematics everywhere. So just let me show you very quickly a view from my university. This is the main campus in the city of Puebla. So I think Puebla is more or less of the same population than Brasilia, about 5 million people. And this is the main campus. But my laboratory is not here. It's 20 minutes by car from the city in a place that is called Valsequillo because of the lake that you can see over here. And my laboratory is here in this lab, in this building that is GrainsLab. This is the website of my laboratory if you want to see more details about the research we are performing. Where you will find some papers related to granular materials, for instance, experiments about cratering and ray systems. Very quickly, just well, I'm going to mention that we have studied, for instance, recently the formation of ray systems that are these strike lines coming from the point of impact and in the Tycho crater in the moon, on the surface of the moon. And we performed some experiments with non-spherical projectiles, so amorphous projectiles. And we observed that the ray systems, for instance, these two that you can observe here in this part, and in this part you can see some rays, and they are produced from the concavities. If you see again the projectile, it has two concavities, one here, one over here, and one over here. And the ray systems are produced by the concavities of the projectiles. So probably in the case of Tycho, also the meteorite that impacted had some concavities, and those produce the rays that you can observe there. So we have also studied recently binary craters. So this is a doublet on Mars. This is a picture from NASA. And you can observe that between the two depressions, there is a strike ridge that is called a septum. And we are able to, well, at laboratory scale, by doing experiments with impact with two projectiles, we perform some experiments and we can reproduce these depressions. And you can also observe this strike ridge in the middle that is produced by the two shock waves generated during by each impact. So there, if the impact is geometric at the same times, so the strike the ridge of the septum is striped. So this means that in this case also the impact, for instance, was totally symmetric. But you can also change delay one impact from the other, and so overimpose one crater on the first one. You can have it totally separated, of course, if you have a large separation between the projectiles. And as you decrease the separation, so you go from two independent craters to overimposed craters, elliptical craters. And something interesting is that when the separation is very small, then you get again a single crater, yeah, and circular with a circular ring. So this is a circular crater. And this is interesting because astronomers were considering that it was weird that about 15% of the meteorites are binary systems. That means there are two meteorites that are falling together, but only 2% of the craters that you can find in the surface of planets and the moon, for instance, they are only 2% are binary craters of this type. So this can explain, for instance, that if the projectiles impact at the same time and very close one to the other, you obtain only a single crater. This can be also observed that in this impact, in the first one that I showed, the projectile was totally amorphous, and even that you cannot see in the final shape of the crater information about the shape of the meteorite because the crater becomes circular. So probably would be something that it's required now to explain is how geometrically, how can you generate in sand by producing a depression, a crater that always is circular independently of the shape of the depression that you are generating. And that can be studied from the point of view of topological, well, probably of geometry only, considering the angle of repose of the granular material. Well, this is not what I want to talk with this. Well, this is only a summary of our study in craters. But in this talk, I want to show some experiments related to liquids. In particular, one that is very, well, I like a lot, that is a triple Leidenfrost effect. And another one that has to do with the discharge of liquid and grains from silos, when you don't have only one orifice, but when you have more orifices. So it's a mixture of liquid and grains flowing from a silo with n orifices. So let us start with the triple Leidenfrost effect. In this video, I'm going to show you, this is you can see there a aluminum plate that is at a temperature 120 degrees Celsius. And I'm going to deposit some water. And what you can see is that the droplets very rapidly evaporates. No? So this is something that is quick evaporation, right? So if you increase the temperature of the plate, the aluminum plate now is at 250 degrees Celsius, probably one could expect that evaporation would be faster. But instead of that, the droplets fall, they touch the plate and rapidly start to coalesce, forming a larger droplet that moves almost without friction with the plate. So this was observed by Leidenfrost a long time ago. And in fact, this is called the Leidenfrost effect. And what happens is that when the water touches the plate, it evaporates very quickly from the bottom, producing a vapor legend, this vapor cushion, that avoids the direct impact, the direct contact between the drop and the plate. Yeah, so the vapor layer is isolates the droplet, so the evaporation rate decreases considerably, and also the friction. Yeah. So the vapor is levitating on the droplet is levitating on its own vapor. If there is a capillary length, that is the ratio between surface tension and the product of density with gravity, density of the liquid by gravity, and this capillary length is is a competition between surface tension and the weight of the droplet. If the surface tension domains, that happens when the diameter of the droplet is smaller than the capillary length. So you have spherical droplets. You can see here the small vapor layer in Leidenfrost. And in this case, you have a large Leidenfrost droplet, but because the diameter is much larger than the capillary length, for instance, for water, the capillary length is about 2.5 millimeters. So this droplet is much larger than 2.5 millimeters, and you can observe that it becomes a puddle. So gravity domains against surface tension. And you can also observe here a vapor layer that is about 100 micrometers. People have studied during the last 20 years considerably the Leidenfrost state. For instance, it has been shown that when you have a large droplet, it has a star-shaped oscillation, and the number of oscillations depend on the perimeter of the droplet. So as you decrease the perimeter of the droplet, the number of oscillations decreases, for instance, from 13 to 10 to 8, and then it continues decreasing until it becomes totally spherical because surface tension domains. Also, it has been shown that if you put a Leidenfrost droplet on a hot plate, but in this case, the plate is not totally flat, but with some zigzag profile, like this ratchet, yeah, the vapor that is expelled from the bottom of the droplet can be redirected and produce self-propulsion. And if this ratchet is now circular, you can generate rotation. For instance, in this video, you can see there the ratchet, and then a water drop is placed on the plate, and you can observe that the droplets start rotating. Yeah. So this is a Leidenfrost rotator. So
this is real time, Felipe, the video.
Yeah, yes, it's real time video. So okay. Here you have another picture of a droplet that is deposited on a flat plate. You can see that it's in Leidenfrost, so it's very quasi-static. And in these conditions, you can measure the evaporation time of the droplet as a function of the temperature of the plate. And of course, close to 100, there is a certain evaporation time for a given volume. And then for the same volume, you increase the temperature of the plate, and it goes practically to 0 because it evaporates very quickly, as I showed you in the first video. And then when you reach a temperature, a certain temperature, there is a considerable increase in the evaporation time. So the temperature at which the evaporation time is the largest, it is called the Leidenfrost temperature. And this is the way you can obtain it for a given substrate and a given liquid. Now, also people have shown that this Leidenfrost temperature can be considerably reduced when you put a liquid droplet on a hot pool of another liquid. For instance, this is a pool of silicone oil. Yeah, so it's very viscous, and then it is when it is at around 80 degrees Celsius only, and you put ethanol, because ethanol is very volatile, it can enter into Leidenfrost on the pool of silicon. Even when the difference between the Leidenfrost temperature, between the boiling temperature of ethanol and the temperature of the plate is only of 8 degrees, because the saturation temperature for ethanol is 72. The plate is at 80, so a small overheating only of 8 degrees is able to produce Leidenfrost state on liquid pools. So all the previous studies that I just shown has to do with single droplets. So one droplet of water or one droplet of oil or ethanol levitating on a surface of a solid plate or a pool of oil. What happens about the interaction of Leidenfrost drops? This is a question that we just wanted to study. And then we observed that in the literature, well, by looking at the literature, there was an article in Journal of Fluid Mechanics about 2014, where they deposit 2 droplets on channels that are overheated, and then the droplets slide due to gravity and collide at the central part of this channel. And then with a high-speed camera, they measure the collision. And they observe that after following the collision, there was a coalescence of the droplets, direct coalescence of the droplets, and then the droplets jump. Because they explain there was a change of mechanical energy, kinetic energy, into elastic energy, and then again this elastic energy produces mechanical energy that propels the droplet, producing jump. But this study was focused only in identical water droplets. So 2 droplets, in this case, they were water droplets of the same size. Then we decided to study our own experiment. This is the hot plate, aluminum plate. You can see the drop 1 at the central part here of a given liquid, and then we are going to deposit another liquid from the edge of the plate. The plate has a small inclination. In fact, it's 1 degree. And then the droplet will slide, colliding in the central part because there is no friction because they are in Leidenfrost state. So the droplet 2 will slide and collide with the second droplet. And all the experiment is filmed again with a high-speed camera. We played with different liquids. So you can see here the list of liquids that we use, 11 different liquids with different properties. So for instance, this is the boiling temperature, its surface tension, density, viscosity, the capillary length for each liquid, and the latent heat. We can notice that the values are not, for instance, for water is not 100, but this is not weird because we performed the experiment in Puebla. So this is the boiling temperature at 2,000 meters over the sea level. This is for ethanol, etc. Then we started by, wondering if all these liquids have a Leidenfrost temperature. So we performed the experiment of measuring the evaporation time as a function of the plate temperature, as the first plot what I explained before. For water, there are the red points. So you can notice that the values of the evaporation time is very, some only seconds. And then at 200 Celsius, you reach the maximum. So this blue point indicates the Leidenfrost temperature for water. We repeat the experiment with all different liquids, but only I'm showing the Leidenfrost temperature. So we found that each liquid has a different Leidenfrost temperature. You can notice the values here. For instance, for ethylene glycol, the Leidenfrost temperature would be about 330 degrees. For all the alcohols, is between 130 and 180 degrees Celsius. Yeah, and then this is the Leidenfrost temperature. So we can plot the Leidenfrost temperature of each liquid as a function of the boiling temperature of the corresponding liquid. Here is water for 93 degrees boiling temperature. You have a Leidenfrost temperature about 200, and for the rest of the liquids. And as a guide to the eye, we put this red line. That is a straight line just showing that the Leidenfrost temperature can roughly be estimated as 1.4 times the boiling temperature plus 50 degrees Celsius. But if we can collapse all this data in a single curve by normalizing the temperature with the latent heat, yeah, multiply it by the heat capacity at a constant pressure of the given liquid. Then you can observe here that all the points collapse. Well, now we know now that all the liquids have a Leidenfrost temperature. So we can study two droplets interaction with all these liquids. So we started with water-water interaction. So you can notice that after the collision, they directly coalesce. If we repeat the experiment with ethanol, direct coalescence also occurs, as in the experiment that we already know from 2014, the article that people had studied before. But what happens now with different liquids? So here we have water, just with a little bit of blue ethanol to distinguish from the other one, blue methylene blue. And then you have ethanol. And in this case, even when the liquids are miscible, because ethanol is perfectly miscible in water, they don't coalesce directly, but they start jumping one against the other. So you can see a lot of bounces. And in fact, the droplets can bounce during minutes, depending on the amount of liquid that you put there. But after a lot of collisions, yeah, there is a moment when the ethanol droplet, in this case, that is bouncing, becomes very small, yeah, and reaches a size at which the droplet finally, you will see, coalesce. So there is a critical size for coalescence, and we observed that it was very reproducible, the size of coalescence. So we wanted to understand why there are bounces if the liquids are miscible, and why they coalesce at a given certain size.
This just a quick question. Can you hear me? So yes. You mentioned that the hot plate had an inclination of 1 degree. So it is a conical plate, so that the drops are always on the center?
Yes, exactly. The idea of the conical plate, well, to the eye, to the eye, it looks almost flat because it's 1 degree inclination, right?
Right. Yeah.
So
Okay.
it's practically flat.
I thought it was the whole table tilted.
Yes. No. The whole table is totally horizontal. So the plate, the droplet is at the center because of this small inclination of the plate.
Right.
The idea is also to have always the collision at the center, that you can film it with a high-speed camera. No? So the high-speed camera is this is a top view. So we are the high-speed camera is fixed, and you only observe the collisions.
Right. Yeah. Okay.
Yeah. Okay. I mean, if you have a plate that is totally horizontal, it would happen the same. Only that after one collision, the droplets will be displaced due to the collision, right? Okay, so that is the idea. So we repeat the experiments with different combinations of liquid, for instance, water and isopropanol here, that are also miscible with chloroform. The chloroform is immiscible with water, but they also happen the same, and with acetone. And you observe that they don't coalesce, even if they are miscible or immiscible in this case, up to the droplets reach a certain size, as you can see here with acetone and water. So again, there is the collision at a certain size when the droplet becomes very small. But there were other cases, like this one, where you have water and dimethylformamide, and where you observe direct coalescence. So we deposit the liquid, and it never bounces. It always coalesces directly, independently of the size of the droplets. So clearly, we had to prepare this table where we have the different liquids against another droplet 1 versus droplet 2. So W is for water, etc., ethanol E, etc. The main diagonal indicates liquids of the same nature. So this is water, ethanol, etc. And you can see that liquids of the same nature, droplets of the same nature, always coalesce directly. While water, basically all the liquids rebound against water, even if they are immiscible. This subscript indicates immiscible. So hexane and chloroforms and toluene are immiscible with water. And you can notice that most of them rebound against water, but toluene coalesce with water. So it doesn't matter if they're immiscible or miscible. It's another thing that is explaining why they rebound or coalesce. Okay, so we follow the dynamics from the moment of deposition of the droplet with diameter d0 up to the moment of the coalescence with diameter dc. So you can see all the bounces by this trajectory. We studied the radius of these bounces from the center of the plate, and we see that it is chaotic. So it's not because of the kinetic energy, because you can notice that at the beginning in time, -20 here indicates the moment in which we deposit the liquid, and 0 is the time of coalescence. So it's a little bit weird to put the time like that, but it's just to indicate that the time 0 corresponds to coalescence. And then here the droplet is larger and has larger bounces, but then the kinetic energy is larger at the moment of collision, but they don't coalesce there. They coalesce even when the kinetic energy is smaller. You can notice also that the diameter of the droplets for each liquid decreases almost linearly up to the moment of coalescence here. So we measure the diameter of the droplets at the coalescence, and it was plotted as a function of the volume of the initial droplet we deposit. So we change the initial volume of the droplets from very small droplets to very large droplets. And we observed that always the diameter of the coalescence was almost the same. This dashed line corresponds to the diameter of the initial droplet. And you can see that there is an evaporation from this dashed line until the moment of coalescence that is shown with the solid points here. Also, it doesn't depend on the initial volume of the central droplet, and it didn't depend on the temperature of the plate. So, well, there was a small dependence on the temperature of the plate, but it can be considered almost constant. So all this give us the idea also that if you see the size of this diameter, it was of the order of the capillary length. So we said, okay, let's plot it the time of coalescence as a function of the difference between the boiling temperature of both liquids. For instance, if you put water against water, all these experiments are against water. So if you put water against water, the difference in temperature is 0. So the time of coalescence is basically 0. The same happens with dimethyl formamide and toluene. But when the difference in temperature is in this side, to the right of this dashed line, we observe bouncing. So this gives us the idea that the important thing was the difference in temperature between the two liquids. So our hypothesis is illustrated in this sketch. You have the central droplet here, that is, for instance, water. So the temperature of the boiling temperature for water is 100 degrees Celsius. And you have a water too, for instance, ethanol, that is at 70 degrees Celsius. Each droplet is individually in Leidenfrost state over a hot plate at 250 degrees Celsius. So here is the vapor layer 1. This is the vapor layer 2. But because the water droplet has a considerably larger temperature than the ethanol droplet, the ethanol also enters or experiences the Leidenfrost state against the surface of the water droplet. So there is another Leidenfrost layer here that prevents the direct contact between the droplets and then preventing coalescence. Because there are 3 different Leidenfrost layers, we call this the triple Leidenfrost state. So to show that, it's easier to do it with a video, but you need to see the vapor being produced during the collision. So we use ethylene glycol, that is the liquid that has the largest boiling temperature, 190 degrees Celsius. And we use chloroform, that is the liquid with the smallest boiling temperature. Where acetone is smaller, but you can notice that the latent heat of chloroform is considerably smaller than the latent heat of acetone, and you need to produce vapor. So you need to produce a lot of vapor, and for that you need the liquid with the smallest latent heat. Yeah. So in this way, we can observe the vapor layer produced there. With the other liquids also exist, but you cannot observe it because the amount of layer, well, the amount of liquid is not visual. Yeah. So to visualize the liquid, we use this ethylene glycol versus chloroform. And you notice there the first collision. So there is no, you cannot observe the vapor that is produced. They are in Leidenfrost, but you cannot observe the vapor. But when they reach the very hot surface of ethylene glycol, there is a vapor layer produced at the contact, avoiding the collision. And then, and a second collision, again, it's coming, and you observe the vapor layer. So this confirms that our hypothesis was right. In fact, this is a picture, a lateral view, where you can observe ethylene glycol, and you observe the small liquid that is more volatile, and you can see that the vapor layer comes from this droplet, from the droplet with the lower temperature, because it sees the hotter temperature as a Leidenfrost surface. So it enters in Leidenfrost state against this droplet also. And this explains several things. For instance, dimethyl formamide, yeah, water and formamide coalesce directly. You can notice that formamide, in this case, has a larger boiling temperature than water. But water has the largest of all the latent heats. So you need a lot of, you need a lot of heat to be supplied to the water to produce vapor. So during this collision of formamide against water, water has to evaporate because it is the droplet with the lower boiling temperature. So it is the one that will enter in Leidenfrost, not the formamide. But water has the largest latent heat. So it cannot produce the considerable amount of vapor to produce the Leidenfrost state with the formamide. And this is the reason why they coalesce directly. We developed a model to study the, well, as I explained you, the moment of coalescence occurs when the droplet that is bouncing evaporates up to a given size. And this size was of the order of the capillary length. So by using a model of evaporation that considers the amount of vapor that is produced in the gas layer between the droplets, minus the amount of vapor that is going out, considering a lubrication approximation for this amount of liquid that is produced in that part. And then we can also estimate the generation of vapor per unit time. And then we have this differential equation that can be put in dimensionless numbers, and you can find the moment of coalescence, or, well, the moment at which the vapor layer attains a thickness of the order of 10 nanometers, at which intermolecular forces are considerably significant, so you can estimate the moment of coalescence. We obtained that it was about twice the capillary length. So these points are for each liquid. So this is this with the properties of the liquid that we found in the literature. We obtained these values are larger than the capillary length that we estimated in experiments, but as a first approximation, we believe that it was a good first approximation explaining this size of the capillary length as the moment, the size of coalescence. After the coalescence, you can observe quick mixing. For instance, if the liquids are miscible, like water and acetonitrile. You can observe explosions, because if the difference in boiling temperature between the liquids is very large, like chloroforms inside ethylene glycol, in this case, then when the chloroform enters in ethylene glycol, it abruptly increases its temperature, producing abrupt phase transition and the explosion. But there were cases where the liquid were immiscible, for instance, toluene and water, but they coalesce because in this way they decreases the surface energy, right? Because they become a single sphere. So they coalesce, but you can notice here, they coalesce, but you can notice that they remain separated. No? This one is the toluene, and this is the water. Here, the toluene was tinted with blue ink, and you can notice them that they remain separated. And because toluene is less dense than water, the toluene goes to the top of the liquid of the water droplet, and then you can transport the toluene inside the water droplet in Leidenfrost state. And this can be useful because toluene is very toxic. So evaporating toluene is dangerous, but evaporating water is not. So you can put the toluene inside the water and transport it on a ratchet, for instance. Okay, this is a summary of what we have done in this work. We show that we determine the Leidenfrost temperature for each liquid, yeah, and a relation between those Leidenfrost temperature and boiling temperature. We show that the Leidenfrost effect occurs between the droplets, avoiding the direct coalescence, even when they are miscible. And the drops finally coalesce when one of them reaches a size similar to its capillary length, because the droplet becomes spherical, and then when surface tension domains, the droplet is spherical, and then the area of contact is very small, and you cannot produce enough vapor to avoid the coalescence. They coalesce. Well, this was published in November 2019, and was covered on Physical Review Letter, so we were very happy because of this experiment. Well, if I have time, I think I have. I have, right, Yuri? I can continue with the second part.
Yeah, you can go ahead. Yeah, you can go ahead.
Okay. So now I'm gonna show you another experiment that we are performing now about the simultaneous discharge of liquid and grains from silos. So like 2 years ago, we started studying what happened when you have liquids combined with grains. Because if you discharge water from a silo, this is, for instance, the clepsydra, that it was the clepsydra that was a liquid, a clock, no? that was built to measure time like 5,000 years ago in Egypt. And the clepsania, or hourglass, sunglass, we could think that is from Alexandria or something like that. But in fact, the only evidence that that exists in the literature is from the Middle Ages. But in the case of clepsydra, you have hydrostatic flow, no? So then you can use the continuity equation and the Bernoulli equation, for instance, for a Newtonian liquid, and obtain the velocity of the flow rate coming from the container as a function of the height of the liquid column above the orifice. So it is hydrostatic. It depends on the height of material above the orifice. But for the case of grains, for instance, in a sandglass, the flow is constant, independently of the height of the water or the sand column above the orifice. So this is can be estimated. The flow rate can be estimated using the Beverly law, This Weber law was proposed about 1962. And it depends on the diameter of the orifice, also depends on the diameter of the particles, but it doesn't depend on height. So it doesn't depend on age in this case. So this in this case is constant flow, and in this case is hydrostatic flow. So the question is, what happens if you mix grains and liquid and you discharge them simultaneously? This happens, for instance, while you in Brazil produce a lot of coffee. So in coffee industry, you have water that used to to wash the grains, and then there is this process to separate the pulp from the beans, and then you have here the seeds, no, that are washed also and discharged. Also, you can find it when beach when there is drag of sand from the beach. You also have combination of grains and liquid. So to study this experiment, we have a cylinder that is our silo. We put some sand inside water, and then we hang the system from a force sensor to measure the weight of the system as a function of time, when it is discharged. And we also film with a high-speed camera to see how the level decreases. So for the case of sand, dry grains, you have the constant flow rate. So the slope of this gives us the flow rate. So the flow rate is constant. For water, you have the red line that is hydrostatic. And for grains, it depends. Well, for the mixture, it depends on the size of the grains. For very small grains, about 100 microns, it is basically constant up to the moment the silo, all the grains end, and only you have the water. So this is again hydrostatic, but the important thing is here. And then if you increase the grain size, you go to another regime that is more hydrostatic. So you go for static for constant flow rate to hydrostatic flow rate. To model the system, we use the Darcy law. So the flow rate for the Darcy law, imagine you have a porous medium. In this case, the porous medium in the Darcy law is a porous medium of length L, in this case, of area A, and permeability kappa. So the delta P is the difference in pressure between this, that it would be the atmospheric pressure, and the hydrostatic pressure that you have here. Then, if you solve for delta P, and using the Kosenik-Karman equation for the porosity, that is this term here, where epsilon is the porosity, that's equal to the 1 minus the packing fraction in the case of a granular material, where we propose that would be the porosity will be given like that. This is the height of the sand, of the layer, that is changing in time, yeah, and this is the velocity of the liquid relative to the velocity of the sand that is also flowing. So this is the reason why we measure the sand level, to obtain this velocity. Then, if you use the Bernoulli equation, that is this one, but the delta P is given by this expression, so you obtain this one. This is the hydrostatic term. This is the hydrodynamic resistance, and this is the kinetic energy term, right, per unit volume. So if you combine this equation with the continuity equation, in this case, using the fact that you have grains at the opening, so you will have only a smaller available area for the liquid to flow, and then you can solve it numerically, yeah, and obtain a solution for the height of the sand level as a function of time, multiply it by the density. By gravity, you can obtain the volume, and then you can have the mass as a function of time. And then show this is the mass remaining in the container as a function of time. These solid points corresponds to the experiments, and these straight lines corresponds to the solution for the case of one orifice. So this was published about 2018. We published this, and we say, okay, this is the case of one orifice, and we can see that our model, even when it is a very simple model, is able to reproduce reasonably well what we observe in the experiments. What happens now for more orifices? That is the problem that we wanted to study now. So this is the experiment, is the same, basically, but now you have n orifices here. I'm showing only the case of 2 in the sketch. Because, okay, if you have 1 orifice, for instance, for water, okay, you have a given time tau. If you have 2 orifices, the time for discharge, these are pictures taken from this time. These are snapshots that are taken, and then you produce these profiles. No? This line corresponds to the liquid level, how it's decreasing on time. So time is in the horizontal edges, and you can hear here the time is tau. So for 1 orifice is tau, for 2 orifices is tau over 2. If you repeat the experiment with dry grains only, then you have a given time tau here at the end of the discharge, and you can notice also that 2 orifices you have tau over 2. So this is expected. No? Imagine you have a tank, and in the tank you take 1 hour to discharge with 1 hole, and I ask you how long will it take to discharge the tank with 2 orifices. You will say, okay, with 2 orifices, it will have only half an hour, right? So it's tau over 2, and that happens for water from dry grains. We agree with that. When you put water and grains, then you observe here that the silo runs out grains at a given time. But then when you put 2 orifices, the time for discharge is not half the time for 1 orifice that would be here, but is considered larger. In fact, if you increase the number of orifices, you observe that the time to discharge, for instance, here for 1 orifice is the blue one, is about 30 seconds. For 2 orifices is about 24. For 3 orifices, identical orifices are around 20. And for 4 orifices, only 19 seconds, something like that. So it saturates the time for discharge as you increase the number of orifices. This is shown here in this plot for different grain sizes, yeah, as a function of n. The orange line is what you expect, but what we observe is that when you increase the number of orifices, the flow rate decreases, and then it becomes basically a little bit more than the flow rate for 1 orifice, and it saturates. So how do you explain that? This is the expected one, as I said, and this is the real one, where the flow n orifice is considered smaller than n times the flow of 1 orifice. So to explain that, our hypothesis, in fact, we are working on that now, is that the mixture, because you have small particles, even when they are not, they are sedimented in the water, they are not flow. It's not a colloidal suspension or something like that. They are sedimented, but even in that case, because they are flowing, there is a small time at which you can consider that they are suspended, and they behave as a non-Newtonian liquid with a shear thickening behavior. So in a Newtonian liquid, if you plot the shear stress versus shear rate, you will find that there is this given by this equation. This is deformation. This is the gradient of velocity on the flow, no? And this is the constant between the shear stress and the velocity is a mu, that is the viscosity. So for Newtonian liquids, this is constant. But for non-Newtonian liquids, for instance, for paint, no, that is a shear thinning, you can start moving the paint no, at the beginning, and then the viscosity is very high. But when you move it, its viscosity decreases. But in the case of shear thickening, for instance, cornstarch, when you deform the cornstarch very slowly, the cornstarch is like a fluid, so the viscosity is small. But if you do it very hard, for instance, if you try to heat in cornstarch, it becomes a solid because the viscosity remains the viscosity increases considerably. So our explanation is that something happens like that in our mixture. When you try to increase the number of orifices, it's equivalent to try to deform the mixture more quickly, and then the viscosity increases. So the viscosity appears in our model in this term, in the resistance, in the hydrodynamic resistance. So what we did is increase the viscosity for the mixture. Yeah? For 1 orifice, we have 1 value. And then for 2 orifices, we increase the viscosity. For 3 orifices, and so on. And we observed that by doing that, we are able to reproduce the experiments that are the color lines with the dashed lines that are the model, increasing the viscosity. So apparently our explanation of our model working with an increase in viscosity considered non-Newtonian liquid is able to reproduce the experiment. This is a work that is performing my student, my master science student, Daniel Rodriguez. So it's in process. We haven't published this, but it's something that we are doing in our laboratory. Well, finally, I just want to acknowledge I had another experiment, but I don't have time to show it. So I'm gonna stop here. This is the people that has been working silo discharge, Andrea Cervantes, that performed the PhD in 2018, doing the first experiments also with granular bubbles. That this experiment I wanted to show, but I hadn't time. She's now a researcher at UADI here in Mexico. Daniel Rodriguez, that is my master science student. Luis Elizondo, that is helping also with the models, a postdoctoral researcher in GrainsLab. This is for the silo discharge. And for the triple Leidenfrost effect, the first part is Jason Palacio, that was master science student, and with two colleagues from UDLab and from the University of Poitiers in France, Florian Moreau and René Ledesma. And finally, I would like to thank CONACYT for the financial support, and you can find more information in my website. And thank you all of you for your presence in this conference.
Thank you, Felipe. Right, so do we have questions, comments? Antoine, do you want to go ahead? Do you have a microphone there? Let me mute here.
I can't hear.
Can you hear me, Felipe?
Yes, now I can hear you.
Nice. Okay, thank you very much for the very nice talk. My question is about the Leidenfrost effect. You mentioned the Leidenfrost temperature, but in the graph you showed, there is also a distribution in the evaporation time. And I wonder if the efficiency of the Leidenfrost effect, if we can call it like that, is different from different liquids, for instance, like the time to evaporate in the Leidenfrost state compared to the evaporation time before we reach this state.
Yes, yeah, the efficiency, as you mentioned, it is different because it depends on the latent heat of the liquid. In fact, it has been it's already known that for the case of a single droplet, this plot is for a single droplet on the substrate, right? So each droplet there for different liquids has different physicochemical properties. For instance, they have different latent heat. No? They have different heat capacity. It also depends on the vapor layer thickness, and it depends on the density of the liquid, for instance, because more dense liquids produce less, the thickness of the vapor layer is smaller because of the competition, because with the weight of the droplet, etc. So it depends on the different factors. But this is well known. There are models to estimate the evaporation time for single droplets. So they depend on different properties of the liquids, and this is the reason why you have different evaporation times. But here you can notice that water, for instance, has considerably larger evaporation time, because as I showed you before in this table, the latent heat of water is considerably higher than for the rest of the liquids. Yeah. So this is the reason why for water you have a considerably larger evaporation time.
Okay, thank you very much.
I don't know if that answers your question.
Yeah, perfect. Thank you very much.
Thanks for your question.
Thank you, Antoine. Do we have more questions? I have a question regarding the Leidenfrost effect as well. When you when you were introducing the problem, my first thought was that there was some sort of Marangoni effect related to gradients of surface tension. So is there an internal distribution of temperature in the grains that can cause let's say, uniformity of surface tension across the surface that would probably make the capillary length something difficult to assign to a drop?
Yeah, that's a good question, Yuri. Thanks for the question. Yes, in fact, people have shown that there is convection effects inside the droplet. So they have put some. I couldn't hear exactly the question because there was some noise. So people probably from the audience online also had the same problem. But if I understood well, you said that there were some convection inside the droplet that could change the surface tension, and then
Yes.
capillary would be difficult to determine. Yeah, that the convection effects, they exist. People have put some particles, for some markers inside the droplets, and they have still single droplets, and they observe these convection rolls inside the droplet. So it exists. We are not considered that in the model. In fact, we are calculating the capillary length as a normal people do. But yeah, probably if that happens, that could help us to understand why our model of evaporation is not able to determine that the capillary length is the size of coalescence. Perhaps, probably that could be interesting to include in our model. We haven't done that, but yeah, because honestly, while I was working most of the time in granular materials, so I didn't realize when we built this with these liquids. In fact, this is my second publication related to fluid dynamics. But I haven't realized that capillary length could be changed because of these convection rolls.
Yeah.
Probably considering that would be interesting.
Very good.
Yeah,
very
good. It would be good to discuss with you about that.
Very good. Very good. Very good. Any more questions? I have a quick question, Felipe. I lost the first part of your description of the collapse, of the cratering, and you mentioned the ray formation. I lost that, so apologies if I'm asking a question that you mentioned, but is there a link between the shape of the object that is penetrating the granular media and the number of rays that you generate?
Yes. In fact, we perform experiments with the spheres with some protuberances to different number of convexities, concavities, and then we found that for each concavity you have one ray. Yeah. For instance, in this case, I don't know if I have the video here. Sorry, I don't have it. Let me check if I have one video that was. No, I haven't in this presentation. But let me, probably I have another presentation where I can show you better for instance, just let me say this one. It's gonna take 1 minute. Oh, sorry. Yes, probably here. You see, if you have a spherical projectile, you don't have rays, right? Because the ejection of material is continuous. Yeah, you have a continuous curtain of ejected material.
It's axisymmetrical.
Yeah, axisymmetrical. But if you have some protuberances like this one, you can see that between the protuberances you have these concavities. So between the protuberances you have concavities. And in that case, you have ray systems, right? There is a blackboard at the bottom, so you can see these rays, right? So we perform experiments with different number of protuberances because from this part, for instance, the material that is ejected is always ejected normal to the surface of the projectile in the equator. Yeah. So the material that is ejected from this part in this direction collides with the material that is ejected from this part, and this generates the rays. Now, if you have a protuberance that's very close to the other one, like this one, this ray will converge with this ray and will form a larger ray. So we show that this is the mechanisms that produce rays in the case of protuberance. Even for instance, for this C star-shaped projectile, yeah, you can notice 4 rays coming each one from this part, because 45 degrees, the ray will be ejected. And we counted with different number of protuberances, and we were able to obtain in fact, well, and this is the video I just showed, showing the two rays. In this case, it would be easier to show in this part. Right? Okay.
Very good. Thank you, Felipe. It was a very, very nice video, very nice talk. Do you have any more questions or comments to Felipe? Well, in that case, go ahead.
No, sorry. I thank you very much, Yuri, for the invitation.
Yep.
It was last year I had here something about our experiments, so I decided today to show more something not about our collaboration that is in process now.
Very good. Yes.
In my part.
It was very nice, and we really enjoyed the presentation of the university as well, the campus and all that. Hopefully, at some point we can go there, and you can come here, and it will be very nice. Felipe, thank you so much. Thank you so much for this talk. It was very nice seeing you, even though if it was online. I think we should thank our speaker again.
Sorry for not being there, but as you know, I had some troubles here, so
yeah, that's fine. That's fine. Thank you very much, Felipe. We'll leave you to it. Bye-bye. All the best. Bye-bye.
Thank
you.
Ciao.
Ciao, ciao. What?
No, I feel like eating tacos.
Tacos and chiles.